we present a novel collision-resilient aero vehicle with a stiff icosahedron tensegrity structure. The vehicle can survive high-speed collisions, reorient on the ground to continue operation, and implement short-range navigations without external sensors. A dynamics simulation is used to predict the deformation and stress during collisions to guide the design process. The simulation helps verify if a proposed tensegrity design can survive a certain collision and protect the vulnerable parts in the shell. The simulation code is available on GitHub. To test its ultimate collision resilience, we dropped the vehicle onto a concrete pavement. It successfully survived a drop from 7 meters with a final landing speed over 11 meters per second. As a comparison, we built a quadcopter with the same electronics and a commercial propeller guard. The propeller guard fractured after a 3.25 meter drop, with a landing speed of 8 meters per second. In addition, we command the vehicle to accelerate and collide with a concrete wall. The vehicle survived a collision of 7.8 meters per second, the highest speed it can reach given the size of our flight space. Taking advantage of its 20-phase geometry, the vehicle can autonomously rotate itself from an arbitrary orientation on the ground to one easy for takeoff. The reorientation is robust against disturbance. In this experiment, the vehicle's initial rotation attempt was disturbed, and it rotated to a wrong face. It was able to continue the rotation and successfully took off again. Using a hopping inertia navigation strategy, the vehicle can perform short-range autonomous operations without external sensing. In this experiment, the vehicle tries to navigate to a goal 3 meters from its starting point, with a series of hops that can help reduce the growth of state estimation error. The vehicle survived the collision, hopped around the tree, and successfully navigated towards the desired target. This experiment validates the vehicle's ability to resume operation after collisions and to navigate with only its onboard inertia sensors in a previously unknown environment.